Yeah.
So thanks everyone for being here. We have a full house today. It's my honor to introduce today's seminar speaker, Dr. Ken Bollen, one of our own here from CPC. He is the Henry Rudolph. I meant to ask him this before I got up here. Immerwahr, distinguished professor in the departments of psychology and neuroscience and the Department of Sociology. He also leads the methodology core here at the CPC. And he's a widely acclaimed scholar. I was just looking over his CV, and his list of awards is so lengthy to recount that it could actually take up the entire seminar and not leave him much time on this topic. But I think what's less obvious from that list is his generosity with students and his colleagues. He's a very active participant in our development course, so I get to hear his insights in reviewing other people's grants quite frequently, and it's always really helpful. And Ken is really known for developing new quantitative methods, probably ones that many of us have now tried, and how those apply to population sciences and behavioral sciences. And those include ways to analyze longitudinal data, creative approaches to measure things that are difficult to account through latent variable type analyses, and the topic of today's talk, how we can start to integrate causal inference. So thank you, Ken.
Thank you so much. Yeah, well, thanks everybody for coming here, and anybody who's on Zoom, I can't tell if there is anybody, but yeah, look, just by way of background on this thing, last year I had a research and study leave, and for years I really wanted to give some more concentrated attention to different approaches to causal inference. One approach that I take is called structural equation modeling. But there's also potential outcomes, and there's DAGs, which is a form of structural equation modeling. And these areas often have adherents who are almost like the Democrats and Republicans, and the rest, insulting each other and, not talking across lines. I personally think that each of these perspectives has a fair amount of value. So I wanted to really dig into it, try to understand each of these literatures. And at the same time, for a long time, I have been wondering what happens when we have binary treatments, binary explanatory variables that we're focusing on. Maybe it's an intervention. Maybe it's an observational study that just is a variable that's created as binary. What are the consequences of using that when you can make a good case that what you're trying to study has multiple values, or is a continuous variable? So this paper's kind of an outgrowth of those two things, where I'm taking each of these perspectives and seeing what the perspective tells me of what happens if you have this binary treatment, and what is its origin, and how does that have consequences for it. I also should warn you that you may find some slides disturbing with equations, so you can feel free to just look away when they come up. But I'll try to. I have them in there for some people, not for everybody. So yeah, let me get started. So I've already told you, I see what we could identify as three approaches to causal inferences: potential outcomes, structural equation models, and DAGs, directed as cyclic graphs. And then we also have these binary treatments. If you read the accounts, particularly of the potential outcomes in the DAGs literature, if you're going to read an article, quite often, probably 90% of the time, they're describing binary treatments. They're focusing on some treatment and some outcome. And the treatment is often presented as binary. So just as some example, you might have a study that's looking at the impact of heavy drinking on education, what happens with it. And they're saying heavy drinking is this dichotomous variables. Maybe they're saying is 4 drinks or more a day is heavy drinking. People who don't have that level are not heavy drinkers, and they study the impact. Or you might have somebody enrolled in a program of one form or another. Maybe it's getting people to stop smoking, and you see whether they're enrolled in this program, and you see what it does to smoking or not. Or you might have the impact of birth weight on some health outcome later in life. And you have low birth weight versus normal birth weight. And you're studying what its impact is. Now, in this literature of potential outcomes in DAGs, there are some papers, which I cite here, that have some discussion of multi-value treatments. But if you go over it, and I think most of you would agree, it's mostly binary variables that they're using. So what happens then if you're using these binary variables, but in reality, it's multi-values of these treatments that are having the impact on the outcome that you're looking at. So it is how many hours of this smoking cessation course, that makes the real difference. It's not just whether you're in the program or not. Or in terms of birth weight and health, what happens if it's gradations of birth weight that really matter rather than just declaring somebody low birth weight and seeing what the impact is. So this is what I'm trying to explore with this. At the end, I'm going to use a well-known empirical example. If you're reading this literature on potential outcomes, to demonstrate some of the results. And I'll also make some recommendations. A little bit of notation here, and this is quite common in the potential outcome literature. I'm going to start with randomization, where we have a treatment that is randomized, and it takes two values. So the randomized treatment is represented by just the letter T, with the 1, 0. 1 is you experience this treatment or receive this treatment or are assigned, if you prefer, and 0 is not. The outcome variable, I'm just going to call Y. To put some names on this, let's say that you're looking at the causal effect of counseling on anxiety. So you have some counseling and you're trying to reduce a person's anxiety. There's a random assignment to counseling. That implies that T is equal to 1. Otherwise, your T is equal to 0. Y is the level of anxiety. But I'm also going to introduce this T star, which is the amount of counseling, how many hours of counseling you receive. But the researcher is just using that T. So what happens when using T in place of T star? Now, the first perspective I'm going to take is this potential outcome perspective. Some people think this is, really relatively new. If you consider a century new, it is new. But Neyman is really the person who introduced this idea, mostly in the context of agricultural experiments. But there's been other contributors to this. Probably the best known is more recent one is Rubin. Rosenbaum, I think, should be getting more credit here too. Rosenbaum and Rubin have done some nice work in this area of propensity scores. But the basic idea is that that Neyman was suggesting. Let's imagine the value that each case would take on the outcome if everybody in the sample received the treatment. And that's what this YI1 is. It's the outcome Y for the ith case when T equals 1. So it just says, imagine everybody received the treatment and what value they'd have on the outcome. And this YI0 for the same people. Imagine the outcome Y for the ith case when they don't receive the treatment. In this case, they're assuming that these variables, Y sub 1 and Y sub 0, are independent of the treatment. So if we said randomization, that's what gives us this independence assumption. We're randomizing the treatment. So the treatment and what value a person would take if they received the treatment and what value the person would take if they didn't receive the treatment are independent of that T. The average causal effect from this perspective is just subtracting those two values. What the value is for these people when they receive the treatment minus what value that same set of people would have if they didn't receive the treatment. Now, what's called the fundamental problem of causation is that in a sample, you can't both receive the treatment and then not receive the treatment. So part of this potential outcome literature is figuring out, well, how can we get these same average causal effects given that condition? And the independence helps. If we have independent treatment, all we have to do is just take the average of those people who are in the treatment group and subtract from it the average of those people not in the treatment. There are some assumptions that go along with this potential outcome view of it. I'm not going to spend a lot of time on them other than this stable unit treatment value. This stable unit treatment value has two components to it. One is the potential outcome for any unit is not influenced by the values of other people in that sample. So there's this type of independence. There's not cross effects across people. But this second component here, there are no different forms or versions of each treatment level which lead to different potential outcomes. You know, this is a more recent statement, 2015. I guess it's 9 years, but this is a fairly recent book in this literature. That second component, which is not given us much attention, you could argue that when T replaces T star implies different forms of versions of the treatment. Remember, T star is the continuous amount of hours or training or whatever you're studying. You could argue that that is a different form of treatment. And in a sense, you might be violating that by using T in place of T star. The other assumption I want to call particular attention to is no unobserved confounders. All right, these are variables that you've left out of your analysis that influence both the treatment T and the outcome Y. And so a question is T star a confounder in a case like this? You know, if T star is influencing the outcome variable and we just have T, is it a confounder? And this is where I find switching to either path diagrams or DAGs is helpful. So this is what's called a DAG. It gets very confusing because the DAGs came after the structural equation models and path analysis. But a lot of people confuse them because the DAGs look just like path diagrams. But they're not identical. There's some overlap, but not identical. These are non-parametric in the sense that it doesn't explicitly give you the functional form of the equations and the relationships between these variables. So it allows interactions and this, that, and the other are all kind of implicit in the diagram. But in the case of the randomized treatment, where we randomly assign a person to this program or not assigned to this program, what we have is that the treatment is going to affect, to some degree, the amount of that treatment a person receives. You know, on average, we'd expect to be assigned to the treatment, and as long as they participate, we'd expect them to be receiving more of that counseling, for example. And then we have the amount of counseling is going to influence the outcome. And there might be some confounders. There might be other observed variables that are influencing both how much of that T star and how much of that Y is there. But because T is randomized, it's going to be independent of the X variable. So just to try to make this a little more concrete, being in the treatment increases T star compared to the control. I had this example of counseling, the amount of counseling impact on anxiety. So the number of hours of counseling T star is affected by you being assigned to the counseling group. But T star, the amount of counseling you receive, there's other variables that could influence that. You might be forgetful. You might be prone to illness. You might be far away from the counseling site. You know, adverse weather. So there's a bunch of things that could affect the amount, the T star value, that's going to affect the outcome variable. Well, or talk, yes.
What if I assign the amount of counseling randomly? Like you get 2 hours, 4 hours, and then the researcher binarized that. to say, okay, I don't want to use the full amount, but then I use the binary version of that.
You still would have the same things of influencing. The T star would differ for those individuals. You can, no matter what value you assign them to, there's no guarantee they would still conform to that.
But then if you go back to the DAG, the error will be the T star will influence the T.
Maybe we could take that up later. Let's just stick with the dichotomy for now. I'm not sure I agree with that, but I think we might get a little off base if we go too far down that. But clarification questions I'm happy with right now. But even in the control group, suppose through work or school, there's counseling available. So you're in the control group, but you still take advantage of it. Your T star value is not zero. You're still going to have a non-zero value on that T star, that continuous amount. So this is the DAG for this. And if and I'm sure some of the people here have worked with it, I'm not assuming everybody has, but part of the task is if you want to know what the effect of treatment is on the outcome, you draw all possible paths between the two, according to the DAG. So we have T to T star to Y, T to T star, X influencing both Y and T star. Again, if you're not familiar with DAGs, this terminology won't be totally familiar to you, but you want to leave path one open because it has the true causal effect. But this path is closed because you have what's called a collider in this path, so you don't have to worry about it. Now, without the DAG, you could, if you're just using intuition, which we do too often in some of our analyses of what we're doing, you might think, well, T's randomized, T star is probably randomized too. So if you thought T and T star were both randomized here, you might mistakenly not put in the X, to control for things. And this could mess you up. This is why I think drawing out what your arguments are is really important here. So if you want to know the impact of T star, which is different than the impact of T, if you want to know the impact of T star, same exercise. Draw out all the paths between T star and Y, and then see what you have to do. That T star to Y, that's just fine. But this second path now, we have to control for X. If T star is in the model, we got to control for X because it's a confounder influencing both T star and Y. Now I'm moving to structural equation models, a third perspective on causal inference. And sometimes the structural equation models are mistakenly described as linear Gaussian. They love saying that, but neither of those terms are right. And I can take that up in the question and answering, but it's an explicit functional form. That is true. When you're dealing with structural equation models, you put in an explicit functional form. And this diagram here in the conventions of structural equation models, boxes represent the observed variables that are actually in your data set. So we got T in our data set, we have X in our data set, we have Y. T star is in an ellipse. That means we haven't measured it. It's a latent variable that has an influence in the system, but we don't have an explicit measure in the system. These two equations are the explicit functional form represented in that path diagram. So they have the same information, is what I'm saying. If you prefer the picture, as I often do, you can just look at that, and not worry about the equations per se. So this then raises the question, I want to estimate the impact of treatment. How can I do it? How can I do it in particular when T star is a latent variable? I don't have it in my data set. All this thing is doing here is rewriting this equation in a what's called the reduced form equation. And if you've dealt with econometrics, you're familiar with that term. All it means is you're just solving out these equations. You're substituting in T star into that equation and simplifying. And what this shows you is that you can just use ordinary least squares regression, regress y on t and x, and you'll get in path analysis structure equation model terminology is the total effect of t on y. In other words, you get the causal effect of the treatment on the outcome that's mediated through the t star. You can't get the t star estimate. If t star is latent, you can't get that. The estimate of t star's impact. You still can get the estimate of t even if t star is latent. And it's just as simple as that regression. Now, occasionally, the t star is available. The empirical example that I'll look at, when I've seen this empirical example presented, I've never seen the t star, the continuous version, its amount of training. In the analyses, people just use the treatment. And I was surprised when I looked at the data set that among the variables that was there was the number of months that each person received training. So when you have an instance like this, when you have both the dichotomized, randomized treatment, and then you have something like how many months they experience the training or counseling or whatever it is, you have an added specification test here, which is kind of interesting. Because if you think that all the influence of this experimental treatment is through the t star, it's how much you're getting of this thing, you can actually test whether there's any path between t and y net of the t star and the x. And that's kind of a specification test in the sense that if that's significant, why? If everything's supposed to be operating through t star, the continuous variable, the amount of counseling you're getting, why would this be significant? It suggests there's something else going on beyond just the hours of training, the hours of counseling, or whatever that t star variable is. So if you have that variable, by all means, you can use it. So let's summarize this first instance of randomized binary treatment. With potential outcomes, you can just do the simple difference in the means of the treatment and the control groups, and this gives you a non-parametric estimate of the treatment causal effect. The directed acyclic graphs tells us that the association of y and t gives us the causal effects without any controls. We don't have to control for anything. But if you want to bring this to the empirical world, you're going to have to declare what the functional form is or come up with some technique that's going to enable you to do some type of non-parametric estimation. The structural equation model is an explicit functional form, and it says regress y on t for the reduced form and get the total causal effect. If t star is available, regress y on t and t star as well as x, and test the coefficient of t, see if it's significant or not. You'd hope it's not significant if your argument is everything's operating through t star. Another aspect of this, the SUTFA, that was that assumption of the potential outcome that I said that there's no other forms of the treatment that have an effect. Well, if we see t star as another form of the treatment that has an effect, that's supposed to violate that assumption, which is supposed to be an assumption for causal inference and potential outcomes. But we can see with the DAGs and the SEMs, there's no problem. It doesn't affect things for getting the estimate of t. All three of these approaches assume no unobserved confounders. So that's the first instance of a binary treatment where it's randomized. That's probably the best case scenario. There is another type of binary treatment, more common in observational studies. This results from collapsing multi-valued treatments into a dichotomy. So years of education becomes, does the person have a college degree or not? So a person, rather than doing an analysis on some outcome, where years of education is what really has the effect, you just say, do they have a college degree or not? And you're using T in place of T star. Or total hours of training becomes, do they have job training or not? Or total alcohol consumed becomes heavy drinking or not. You know, a certain threshold, they're coded as a heavy drinker. So the question is, what happens with that? Now, sometimes T-star is not collected, but the treatment variable is available in the data set. So a survey might just ask, is this person college educated or not have years of education. So the crude measurement of T-star might lead the researcher to use T, or a person may believe, oh, this dichotomy is a lot easier to use. And you know, CPC has this interesting mixture of people from health, background and social science background. I can tell you from my background, it drives me crazy when you have these beautiful continuous variables like blood pressure or birth weight or whatever, and it's collapsed into a dichotomy. We're striving in the social sciences, trying to get something that approximates a continuous variable. And here you have it, and it's, just making it into a dichotomy. So what happens when you do that? What happens when you use T in place of T-star? Well, confounders remain an active threat in observational studies like we're talking about now. This most often occurs in observational studies. And assignment to treatment is important to model. So what you see in this potential outcome. So again, I'm swinging back now to the potential outcome perspective on how to handle this problem with a different type of binary variable. So if you have this conditional independence, if you can say that I've got a bunch of observed covariates in my study, and if I control them, then I'll see this independence of Y1 and Y0. The outcome if everybody received treatment and the outcome if everybody did not receive treatment. It's the same set of assumptions we talked about before, but we do want to call attention to this last one, no unobserved confounders. So in this study, we're just analyzing T's impact on Y. We're saying, well, we're controlling for X. We still got this T star. So the question is T star a confounder or not? Because this is a fundamental assumption of the potential outcome perspective. This again is where turning to these diagrams from DAGs or SEMs, I think can be quite helpful. Here's a DAG for it. T star, remember, is this continuous number of hours or years of education, and we're dichotomizing it into a college degree. So T star now is being collapsed, often in a nonlinear function, into a dichotomous treatment. And it's T star that influences Y, and this X, which is a confounder, is influencing both T star and Y. Now, if you were a real purist from the DAG area, you would say, Ken, that diagram's wrong. You shouldn't have T in there because it's non-parametric, it's supposed to cover any nonlinear function of T star. And T is just a nonlinear deterministic function of T star. But I think it's more helpful to show it here than to not. And so let's see, what happens with that. DAG shows to get the causal effect, we need T star influence on Y. It requires the control of X. So if we want to know T star's impact on Y, it requires the controlling of X. The T, the binary variable that you've created, has zero impact on Y. In this situation, T star is an unobserved confounder because it influences both T and it influences Y.
Oh, not to be totally annoying, but just to play like devil's advocate, since you're using the case of education, it's like there definitely would be a threshold effect of the college degree. So even thinking about that as an example, we want to think about how the continuous approach is missing the role of credentials and outcomes. So like would have to be theoretically.
Yep, I have that as my example in this paper that's published. I didn't mention psych methods, it's online now, but I used that exact example, that you could have both years of education and the degree, sort of a degree effect at the same time. So I would agree with that. But let's look at birth weight or something like that. You know, birth weight is T star and you just classify as low birth weight. You know, I don't know, maybe you're arguing it's a more complex functional form between T star and Y than just a linear form, and I would agree with that. But T has no effect on Y once you control for the person's birth weight with the proper functional form. And we go through a whole bunch of other examples that are like that. And what I find so ironic is that by using the binary variable, you're actually violating a key assumption of both the potential outcome and the DAGs and the SEM of an omitted confounder, because it meets the classic definition of confounder. The continuous variable that has, if it's the continuous variable that has the influence on the outcome, and you're using a collapsed version, you've actually left a confounder in there. Now, if we commit to a functional form, and this is how you represent this in a structural equation model, T star, again, I'm assuming is unobserved. So I have a T star and an ellipse. That crooked arrow to T, that's just as representing a nonlinear connection between the two. As T star passes the threshold, T is coded 1. If it's not below that threshold, it's coded 0. So this is the representation in the SEM. Here are the two equations that correspond to that. If you regress Y on T and X, you can see from this diagram too that T star is a confounder that could bias the causal coefficients for the T and the X. Again, it's consistent with the idea that T star is a confounder in this SEM as well. Now, what is interesting is that with this explicit functional form and using a very old technique that I think is not studied as much in a lot of disciplines now, but there's a wonderful thing called specification analysis from an econometrician, Henry Tile, from 1958, if I'm remembering the year right, who shows what happens to coefficients in equations if you omit a variable or if you bring in an excess variable. And so what I'm doing is taking these ideas about omitted variables and applying them to our situation here. So the correct model is Y is regressed on this T star and X, but you estimate Y regressed on T and X. So you're going to get some coefficient on T. If we had control for T star, that coefficient should be 0, but you're going to get some kind of coefficient on that thing. And what this does is it shows you what you should expect the coefficient to be. This probability limit just is a statistics term, just saying what happens if the sample gets really large? What does it converge to? And it will converge to, the coefficient on T will converge to this little b T star T times b y T star. You could argue what you really want is the impact of T star on Y, and that's that by T star. Well, you're going to get that coefficient multiplied times b sub T star T. And what this coefficient is the coefficient you get when you regress T star on T and X. It's just an analytical device to show you what you're going to get. And the bias is not limited to just T's coefficient, X's coefficient. The variable, there's nothing wrong with it. You got the correct confounder in there. Its coefficient is going to be biased too by the fact you left out this T star. It's not immune to that effect. Now, what I did here is I just had one generated data where I just generated in a sample of 1,000 people the true model where Y is influenced by T star with a coefficient of 1, and it's influenced by X with a coefficient of 1. And I just saw, all right, well, what would happen if I now collapse T star into T, and you can see that I'm getting a coefficient 40% higher than it should be for the T star. So we know this thing's true effect is 0 once we control for T star, but when you do it, use this collapsed version of the variable, you're actually getting a coefficient that's a lot higher. This column right here, let me just briefly mention, I don't know how much time I'll have to do this, but what is counterintuitive and kind of cool is that you can estimate the impact of T star even if you only have T, even if you only have the treatment variable and don't have T star. There's an approach to categorical data in structural equation models where you assume there's an underlying continuous variable. You have to make a distributional assumption for the error term of normality. But if you make that assumption, we get a damn accurate estimate of what that coefficient is. It's, it's 1 in the true generated model, but just using the T and using this diagonally weighted least squares SEM estimation is what it's called. I can get a pretty good estimate of it. I'm doing that here because in the situation when you don't have the T star and you really think it's the T star that's doing the influencing, you don't have to give up all hope. There is a way to try to get at that, even with your categorical variables. So let's look at the summary. Binary treatment via categorization of treatment, right? We don't have the randomized T anymore. We've got an observational study, and for whatever reason, you categorize your treatment variable. And it's really the continuous variable that's having the influence. Potential outcome perspective, T star would be an unobserved confounder. The simple difference in the means of the treatment and control group gives you a biased estimate of the treatment causal effect. You got a DAG, it's sort of showing the problem in a graph. If you have a structural equation model and you're comfortable with the explicit functional form, if you just regress y on t and x, it gives you bias effects, and we actually have some expressions for the nature of that bias. But if you take a latent variable SEM approach, you can actually estimate the impact of T star when only T is available. Now, this is the empirical example I mentioned, and this is very widely used in the literature. A job training randomized experiment. He seeks the causal effect of job training on post-treatment income. It consists of a sample of men with a poor labor market history, 185 men randomly assigned to a job training program, 260 to a control group. Y is the natural log of real labor market earnings in 1978. T is the true, randomized binary treatment to job training or control. And in the data set, I was so delighted to see they actually had months of training in there. So they had the T star in there. X is a whole bunch of variables: age, years of education, past earnings, unemployment, no high school degree, etc. If you take a potential outcome approach, which we could because we have this randomized treatment, without any controls, we'll find that the difference of the training is about $1,300. Not too different with another potential outcome approach called regression adjustment. Comes to 1231, versus 1278. It's very close. With the structural equation model, if you take the explicit functional form, T star is an observed confounder of Y and T. You would get the biased results on this, but you also, because the T star is available in this data set, we can do that empirical test I talked about. With these data, just to see if everything's operating through the months of training. And here in this regression, let me focus on the second column, right? The second column, I'm just using the T star, the months of training, as the predicted impact. And you can see it's coming in statistically significant at conventional levels. But column 3, what it's doing is it's doing this kind of extra test saying, all right, T star has a significant impact. does T have an additional significant effect if I enter it into the model? And you can see it's not even as large as its standard error. So this is actually reinforcing the idea that it's the months of training that's having the impact. That's where this causal flow is going. It's being allocated to this program and then how many months of training that leads you to have. Okay.
Can I answer a question?
Sure.
If I care about the effect of T star on Y, and then T is randomly assigned, and I believe the structural equation model, why can't I use the T just as instrumental variable for T star, and then use IV instead of
You could. If you wanted to use it as an instrument, if you suspected that there was, let's say, a correlation between the error of that equation and this T star, you could exactly do that. But that, right, to justify it as an instrument, right, it is assuming that there's no association.
Yeah, that's the
Yeah.
assumption, right? T doesn't have a direct effect on Y.
Exactly,
Yeah.
exactly. Because there's only one instrument here, you couldn't do the over-identification test. But you're right, that you could use it as an instrument. Now this one, so this is the repeating what I had in that first one. I had the T star, and it's the same coefficient for the impact of that training program, how many months of training there is. The second column is if you just put the treatment in, what coefficient you would get. And the third column here, that 0.337, well, since I had this T star in this data set, I thought I'm going to play around with this. Suppose I did what people often do, and I collapse that T star into a dichotomous treatment. And I arbitrarily say they have to have at least 18 months. If they have at least 18 months of training, I'm going to count them as getting the treatment. If they have less than 18 months, I'm not. Well, look, I get a coefficient 0.337, which is about, what, 50% bigger than what I get with the randomized treatment. Alternatively, if I say, well, it should be 12 or more months, I get something that's close to the original. So, what does this illustrate? It illustrates that, well, maybe you could get lucky and you'd get the same value if you collapsed to, as the randomized treatment, or you could be unlucky and get something that is really biased compared to what it should be. So let me conclude. So going through this exercise still left me to feel that each of these perspectives was helpful for me understanding this problem. But it also convinced me there's insufficient attention to the types of binary treatments. The binary treatment's randomization of treatment is one thing. Multi-value treatment collapsed into a binary treatment is something quite different with different consequences. The randomization is the cleanest situation, as you probably would not be surprised, but we've got lots of instances with observational data where we're using binary variables to try to assess the impact. And in that case, where you have observational data and you've collapsed into a binary treatment, the T star becomes an unobserved confounder. You're contradicting the very, assumption of the modeling approach that you're taking. Also, this latent variable SEM can estimate the impact of Y on T star and X, given a consistent estimate of that latent T star and observed T. It assumes an explicit functional form. So the best situation is what I had in this empirical example. You have both T star and T, because then you can do this kind of diagnostic test as well to see if all the influence is through T star in your model. This is just a table summarizing in a more non-parametric form. This is more nuts and bolts. So treatment variable available, only T, T and T star. So if you only have the T variable available and you have randomization, you can just regress Y on T and X and you're in good shape. If you have binary treatment via application, right, and you only have T available, this is just showing the commands to get the results that I was reporting there in a SEM package called Levon that's available in R. All you have to do is declare that this T variable is categorical, and the coefficient you'll get out of this will be a consistent estimator of the T star impact. So even if you don't have that T star, you can actually have an option to get the estimate of the T star's impact. If you have both T and T star, if it's a randomized binary treatment, you can, interestingly, do a regression on both T and T star. Make sure that the T coefficient is not significant. No, if it is significant, you got to ask yourself why. If everything was supposed to be operated through T star, why is T significant? You also can see how T star is related to both T and X. So the amount of treatment, how closely predicted it is by that treatment. If it's binary treatment via categorization and you have both these things available, then it would just be Y on T star and X. And you also could see T star on X. So I guess my most basic conclusion is not all binary treatments are created equal, and we shouldn't treat them as such. So I welcome any comments or questions.
Really enjoyed the talk. Take the job training example. Just what if we imagined that there was a unobserved confounder like motivation that moderated the effect of the treatment? Like, I mean, so we're getting like the average treatment effect, estimate, but in fact, maybe it was like the motivated people had an effect and unmotivated people maybe had a negative effect such that they like canceled out. Like there was, and it's sort of realistic, like treatments, some people like randomized roommates. That's like, it's a treatment, but it depends on how well the roommates get along. So there's some like endogeneity coming on there too. So how would you, like intuitively, like how would you deal with even exploring whether there might be like heterogeneity of the treatment effect itself, just to get a sense like empirically of what the best kind of approach would be.
Well, first of all, there's no magic to any of these techniques, right? You've got to have, if you have unobserved confounders, as you're describing, you can't do much about it. If you can create a model such as that T to T star to the outcome variable that's over-identified, you do have that extra test. So if you find that T to be significant in that regression, and you don't have a good explanation for it, it could be something like you described. It's pointing to a potential problem with it. I don't know how much I would trust it, but if you did have individual differences in the coefficients, that will create heteroscedasticity if you assume that there's just a fixed coefficient. There are heteroscedastic tests, but I'm not sure how much I would trust them for their exact nature. But yeah, I mean, if you've left important characteristics out of it and you just have an exactly identified structure, you're still going to get bad results. This is more like knowingly creating a problem. When you are dichotomizing this thing, you've created an unobserved confounder. Yeah.
So it seems like fundamentally we need to know whether we hypothesize a dose response or not. Right? So if we think there is a dose response and the amount matters, then we shouldn't choose a binary intervention. We should give a dose. And if we come up with the right functional form for the relationship between the dose and the outcome, are we still going to get bias?
No, if you have the correct functional form, the amount of dose, to that outcome, no, there shouldn't be. With the usual qualifiers that you have the other unobserved confounders in there.
So I mean, isn't that a reason why we wouldn't ever want to make binary variables out of our continuous variables? Like if we think there's a dose response, we just wouldn't do that.
Right, but I see numerous instances, so the examples I gave you were not pulled out of the air. You know, I was just looking at articles I was reviewing and they're giving me examples of that.
Yeah, I mean, it seems like from the health field, we're based all the time with kind of public, what we think are publicly. We define risk factors based on cut points. Just to be able to more clearly convey messages
Yeah.
about. So we're kind of forced to do that to make our results more interpretable. But obviously that has its downside.
Yeah, there's a lot that follows with the collapsing, right? So if you're just, suppose you're just a little over the border for high blood pressure, you get this whole medical regime thrown at you, right? If you're a few points below that, you wouldn't necessarily get it. So it's just a more conscious kind of thinking of it. I mean, yes, for communication, I understand that. But when we take that communication aid and then put it into these more formal models, when we don't have to, that's mostly what I'm talking about.
In my response, I think some of your responses, we do that sometimes because there are threshold responses, and so is it better to dichotomize, or is it better to just put a simple continuous variable? I would argue that dichotomizing, if there are a threshold response, best response would be splines and multiple orders of polynomials, but like you can't always do that depending on the amount of data you have. So I think you were getting at that point earlier, and so I think that's why we see college, some of these things dichotomized the way they are, because it's a simple, crude way of trying to deal with that. I liked your examples of the months in the Lawn example paper that they, the months in that program made a lot more sense to me. I think the college one in mine made a little less, because it's just sort of a crude way of dealing with pressure.
I would agree with you on the college. When I used to teach the linear regression course in sociology, one of my favorite examples to use is I would have them estimate income regressed on not only degree, but years of education, because they had both of them there and they both came in significant.
Yeah.
So there was kind of a credential effect as well as the years of education. So I would agree the education, the college one's not the best example, except it is still true. If you only use college, then years of education could be that omitted variable. If you only use years of education, then the degree might be the omitted variable.
So in the first example with randomization, going on this counterintuitive, that's an example of things like fidelity or intensity effects that you're missing or non-compliance issues. So those are the kinds of things where you would get the randomizing to treatment or not, but then actually it's a whole lot more complex than that. And so you would be missing that, and it would be, I think you're making the point about if you randomize, aren't they getting it? But is that the kind of issues that you're sort of addressing with that case?
Yeah, the randomization is the best, situation, because you are going to get, if it's, a good randomization, right? You are going to get the impact of being in this group, or if there's multiple groups, of those things. But if you also are interested in whether it's the amount of whether you're trying to administer to those people, you can't get it from that. It would be the reduced form equation, for the randomized treatment. So yeah, I would much prefer that to the observation, if I could have a choice. But sometimes we don't have a choice. A lot of things I work on.
I was just thinking some more about when you were talking about having T and T star in the equation, we would expect T to attenuate to 0 if it's all operating through T star. And the example we just talked about, the example you used in your class where you have T and T star, you have both significant effects. I'm wondering, like, is that an example of when you might expect or even desire to have both of those? Not that you would be, attached to any particular outcome, but like, if you do hypothesize that it's operating through both threshold effects and continual effects, or what are the situations under which you would expect that to not resolve to 0?
Well, like you just described, we have pretty good arguments about credentialism, right? In the social sciences, how the credential could actually have a difference above and beyond the years of education. So if you have good theoretical arguments to suggest that at this point, something separate happens or some symbolic meaning that's assigned to it. Those should be the cases. It's not that, I don't want to say that it's always going to be wrong if you find the treatment still has that effect controlling for T star. I'm just saying you got some explaining to do. If you didn't come up with some explanation for it in advance.
Hi. So, great, it's great to see this. I want to follow up on the question that was just asked. Why is that not a functional form issue? Because you could imagine modeling the effect of years of education in such a way that you would capture those thresholds. So I guess I'm wondering what's the difference?
Well, in some ways, I would say the difference in the educational example is that, as I understand, it's not my specialty, but there is this credential argument, so there's theoretical explanations for those particular points. The more general functional form argument, it could occur, but what are the odds that you chose your cut point right to pick those exact points where the curve is kind of changing around? That could be the explanation. This is why you should do good diagnostics. Plot the residuals with that continuous T star, with the other variables. See if you see some kind of sharp jump or decline or whatever on that. So it could occur, but it'd be more coincidental. Whereas in the educational example, we were saying 12 years. We were saying 12 years, 16 years, graduate degree. Who knows? Maybe it was true. No, I shouldn't say that. But, we have the explanation for it. We have some theory behind it. It's really, when it comes down to it, right? It's just giving more thought. Does this really make sense? This dichotomized treatment that we're looking at? What are the costs of it? Is it really the driving force that's going to influence, that outcome? And to reinforce, it's not just the treatment effect that you're estimating that's going to be messed up. It's the other variables, your control variables too. They're going to have bad coefficients, as long as they're correlated with that T star variable.
Any last questions? I think we're good.
Good.